Hey everyone, and welcome. Today we're going to talk about something that powers our world in ways you might not even realize: heat engines. Now, these are amazing devices that basically turn heat into motion, and you'll find them everywhere, from inside your car to the very coastlines of our continents. Okay, let's get into it.
Think about it. It sounds like magic, right? A little spark, a bit of fuel, and all of a sudden this massive 2-ton hunk of metal is just cruising down the road. This is the perfect place to start because the car engine is probably the heat engine we're all most familiar with, and it holds the secret to understanding this whole thing.
So to solve this mystery, we have to pop the hood and see what's actually happening inside. We're going to break down this rhythmic 4-part cycle that is literally the heartbeat of an internal combustion engine.
Okay, so this whole thing happens in 4 quick steps, over and over again. First, the piston drops, sucking in a mix of fuel and air. That's the intake. Then it shoots back up, squeezing that mixture into a super tiny space. That's compression. Right at the top, a spark plug fires. Kaboom! That explosion creates this insane heat and pressure, which slams the piston back down, and that is the power stroke. That's the moment that actually moves your car. Finally, the piston rises one last time to push all the used up gas out, the exhaust stroke, and the whole chamber is ready to do it all over again.
So we've seen how a car does it, but what's really cool is that the car engine is just one specific version of a much bigger idea. Let's zoom out and look at the fundamental recipe that every single heat engine, no matter how big or small, has to follow.
At its absolute core, this is all a heat engine does. It takes thermal energy, what we feel as heat, and it transforms it into mechanical energy or work, which is really just a fancy way of saying motion. It soaks up heat from somewhere hot, turns a part of it into useful movement, and then it has to dump the rest.
And every heat engine needs these 3 things to work. You've got to have a heat source to provide the energy. In our car, that's the tiny gasoline explosion. You need a working substance. That's the fuel-air mix itself, the gas that expands like crazy when it gets hot. It's the thing that actually does the pushing. And finally, you need a heat sink, which is just a cooler place for all that leftover, unused heat to go. For a car, that's just the world around it.
But here's where things get really fascinating. It turns out this whole heat-to-motion conversion, it's not a perfect process, not even close. In fact, it's like the universe demands a payment every time. Every heat engine has to pay this kind of tax that it absolutely cannot get out of.
For a regular gasoline car engine, that number, that's its efficiency. Yeah, that means only about 20% of the energy that was stored in the gasoline actually gets turned into the force that moves your car forward. So the big question is, where does the other 80% go?
This funnel is the perfect way to picture what efficiency really means. It's just the ratio of the useful work you get out, that little stream at the bottom, compared to the total amount of heat energy you pour in at the top. So for our car, for every 100 units of energy we put in as fuel, we only get about 20 units of motion. The rest? It's just lost, escaping as waste heat.
Now here's the crucial point. That missing 80% isn't just because of bad engineering. It's a fundamental rule of the universe, described by the second law of thermodynamics. It basically says that every time you change energy from one form to another, some of it is always going to escape as useless, disorganized heat. You can never ever build a 100% efficient heat engine because you can't stop this natural tendency for energy to just spread out.
All right, so we've seen that every engine, from a car to the cosmos, needs a hot source and a cool sink to work. We've gone from a tiny piston to the laws of physics. So now, let's see what happens when we take that exact same principle and apply it not in a little metal cylinder, but on a planetary scale.
The answer, which is pretty amazing, is yes, absolutely. That daily cycle of breezes you feel at the beach, that's actually a massive natural heat engine at work. Let's break down how this uses the very same ideas we just learned.
The secret is all about something called specific heat capacity. Now, all that means is that land heats up and cools down way, way faster than water does. So, when the sun is beating down all day, the land gets hotter quicker. And we all know hot air expands and rises. This creates a pocket of lower pressure over the land, and that temperature difference is the key that starts our giant engine.
This table perfectly lays out the engine's daily cycle. So, during the day, the hot land becomes our heat source. The hot air rises, creating low pressure, and the cooler, denser air from over the sea, our heat sink, rushes in to fill the space. That's what we call a sea breeze. But then at night, the whole thing flips. The land cools down super fast, becoming cooler than the sea. Now the air flows from the high-pressure land to the lower-pressure warmer sea. And that's a land breeze. It's a giant natural engine, switching on and off with the sun.
So let's bring this all home. We've gone on a journey from a tiny, man-made piston all the way to the massive winds that sweep across our planet's coastlines. And through it all, we've seen one single, universal principle at work.
This is the big takeaway. This is what it all comes down to. Whether it's the super intense split-second temperature difference from an explosion in an engine, or the gentle, all-day temperature difference between the land and the sea, the result is exactly the same. A difference in temperature, a heat gradient, is what drives the flow of energy that we experience as motion.
So the next time you feel a cool breeze at the ocean, or you turn the key in your car, you'll know that you're watching the exact same fundamental principle in action. The universe is just full of these engines, constantly turning heat into movement. The only question left is, where else will you spot